about doing a hands-on approach to this course, and I've got to tell you that hands-on is really not something that's possible. And what's the reason for that? Well, this course contains a lot of theory, okay, and basic information, so that you can deal with the question bank, because the question bank is really what determines you know, whether you're going to get your ticket or not, okay, passing the question bank. And so this is what we talked about last time, about when you get 3/4 of the way through, you're going to focus on the question bank, okay? So that's why the course is the way it is. In terms of hands-on, that's not a possibility, because when you go and buy your radio, you will find that although they have a lot of very similar features, they're really different. I use a Kenwood, and if somebody gave me an ICOM radio, I really could not use it. I would have to read the manual from cover to cover to be able to use it. It's like the difference between, you know, a PC with Windows 10 and then going to Linux, right? It's a totally different operating system. So it's the same with when you buy a transceiver. The transceiver is different. So we can't really give you a hands-on. We can give you the theory, and then after this course is over, we're going to give you a how-to ham course. Okay? Oh, somebody's trying to get in, yeah. We're going to give you a how-to ham course, which is going to be just 3 or 4 Thursdays, and we're hoping to bring out the Northern Director of Radio Amateurs of Canada for that how-to ham course. He's going to give you a lot of the latest in electronics, and he's going to try and convince you to become a member of Radio Amateurs of Canada. Well, the great news is, when you get your certificate from Radio Amateur, from the federal government, Industry Canada, they will give you a form with that certificate from RAC, Radio Amateurs of Canada, and you get 1 year's free membership in Radio Amateurs of Canada. Isn't that great? Okay, so that will take care of that, but he will explain RAC. Okay, we got somebody coming up. Hey, great, we didn't lose you. Okay, now, so that's the explanation there. Okay, and are there any questions or any concerns that anybody has at this point? Anything that anybody wants to ask before we start?
About this?
About the course,
okay.
how it's structured, and
I got questions.
electronic questions?
This specifically? No.
Okay, so yeah, Tony will answer any questions concerning electronics or whatever. Okay, so that's that. Now I'm going to introduce to you Tony VE3 DWI. And the great thing about Tony is he's got, I believe, 30 or 40 years experience in the radio field. So this is why, as I said last time, we want you to interact with the teachers, because they've got all this experience, and you can't get that type of interaction off a CD. Okay, this person who knows everything that he knows about radio. It's just a fantastic font of knowledge. He says, "Don't build me up, Bruce. I don't like it." That's what he always tells me. Anyway, so I'll pass it over to Tony.
Okay, thanks, Bruce. Don't believe everything he says.
No, just half.
Alrighty, I got some handouts here. You want to pass them around? This is one handout, okay? So just pass it on.
Each one's okay.
Oh, okay.
It's one package, 2
Yeah,
sheets.
it's a complete set.
That's it.
Okay.
That's it for this side.
And then we have
Oh, that's it for this side.
That's it for that side?
Let's roll it.
that side.
Oh, sorry.
Okay, that's a complete set.
Then you don't-
Pass it on. And here, and here.
I'll
We
need one more.
more.
You don't have one now.
All set? Wow. Can't believe it. I didn't even count. Alrighty.
Do you need me again?
Well, as Bruce said, my name is Tony, your last name is Lelyveld, that's a Dutch name. So I came to Canada with my wife and 3 children in 1970, and we've been here ever since. So if you hear a bit of an accent, you know where it came from. You also may find I'm standing crooked because I threw my back out a couple of days ago. So, call sign Victor Echo 3 Delta Whiskey India. You're going to learn all these NATO codes. VE3 DWI, Victor Echo 3 Delta Whiskey India, driving while impaired, driving while intoxicated, driving while incontinent, whatever you want. You will find on the back of one of these sheets the entire NATO code alphabetically with pictures with it. So you've got to learn this whole NATO code, Alpha, Bravo, Charlie, Delta, Echo, Fox, Golf, Lima, Mike, November, you name it. It's on there, so this is a handy thing to make you, well, not to make you learn it, but it comes in handy, it's all there. Alrighty, well, there's 3 items I want to mention first of all. There's no such thing as a stupid question. The only stupid question is the one that's not being asked. Secondly, energy cannot be destroyed, and you will find that throughout the course in a sense. In one of the sentences in the book here, I read that energy is lost in heat. Well, energy is not lost. Yes, a resistor dissipates heat when you put a current through it and a voltage across it, but that heat, that energy is not lost. It is converted or transposed in the form of heat, which is again absorbed in the atmosphere, it heats our surroundings, etc. Heat warms up the sky and creates condensation over time, and it falls down to rain, so that there's a complete cycle. Energy is not lost. It just transforms into a different form of energy. Because if energy would be lost, we would eventually run out of water, right? But water is always recycled, so think of it that way as well. Energy is not lost in the form of heat. Your light bulb, yeah, gives you a lot of light, but it also gives heat, and people say, so the light bulb is inefficient, because, yeah, it gives less light than the amount of power we put into it. But in the winter, the heat that comes off the light bulb helps you heat your house as well. So again, there's another transformation of energy that is useful. All right, tonight we're going to be teaching Ohm's law, and it's actually not that hard. There are various ways of learning it and remembering it. The first of all, what I want to explain is Ohm's law is a little bit associated with a garden hose. We have a garden hose, we hook it up, turn the tap open, there's a certain amount of water flowing through there. The garden hose represents also a resistance on the inside of the garden hose. The walls resist the flow of water. So that's like a resistor. If you want to put more water through it, what do you got to do? You got to put more water pressure on it, right? To get more water to go through the hose. It's the same with a resistor. A resistor, when you apply a voltage across it, it'll cause a certain amount of current to flow. If you want that current to become larger, to increase, what do you have to do? Open the tap more, in other words, increase the voltage. That allows more current to flow. If you want more current, increase the voltage or decrease the resistance of the resistor. So they're all interrelated with each other. The first chapter that was taught there on Tuesday, you probably heard about resistors and you've seen some pictures in the book. I have a few samples here. I'll just pass them around and you can have a look at them. Here is, for example, a carbon resistor. This is about a quarter watt, I would say, maybe half a watt, I'm not sure anymore. But that's a fairly small resistor, physically. Resistance, you have the color code on there, so you have to figure that out. Here's a resistor that's a wire-wound resistor. It can dissipate a fair amount of power because it is wound on a ceramic body. As you can see, it's a ceramic tube. That's where the wire is wound on. And, I've got to look over the top of my glasses here, this is a 10 watt resistor, which means it can dissipate a power of 10 watts. Doesn't exactly say how many ohms it is, but anyway, so here's a couple resistors. Here's another one, that's another power resistor which is on a ceramic body, and so it can dissipate quite a bit amount of heat actually. This one is 30 ohm with a tolerance of 5%. And here's another one, 3.5 ohm, 5%, 5 watts. It can dissipate 5 watts. So we'll talk about that a bit more in detail, but it gives you a bit of an idea of what resistors can and look like. Here is a carbon resistor, and that one is a 1 watt resistor. So you can see with the smallest resistor there, which is a 1/4 watt, and this is a 1 watt. So this resistor can dissipate an amount of power of 1 watt. If you were to increase the voltage so that your current becomes larger, you're going to exceed the capability of this resistor, and what it will do, it will burn up. You've noticed that in certain electronic equipment that when you put too much power in, a resistor burns up, that things don't work anymore, and because you let the smoke out. Every manufacturing process, they inject a little bit of smoke in resistors, transistors, capacitors, and when you let the smoke out, it doesn't work anymore. So it's actually smoke that makes electronic force. Of course, I'm kidding, you know. All right. What's the symbol of a resistor? Do we only have a red pen, Bruce? That's all we got? Oh, looks like it. Omega. That's an alphabet, the Greek alphabet. Yeah. That's a symbol that they use to indicate resistance. The symbol for a resistor, actually as a schematic symbol, it is presented like this. European standards, they often do it like this as a resistor. And the symbol for resistance, that's the gentleman there, Tyson, okay, is the Greek character omega. So we just call it ohms. A resistor has a value of an X number of ohms. What is an ohm? A resistor of 1 ohm with 1 volt applied to it will have a current flowing through it of 1 ampere. 1 amp. So that is the Ohm's law. Voltage equals I times R. Okay? And also I encourage you that you study, at least every day study some, and that you study the chapter that you're going to get, like
This is like a heat sink. Okay, to dissipate the heat. But this
I
is depending on what's
equals
inside of it, that's why
E
I think
divided
because
by
this is
R,
what they give up.
So
and
basically,
R
this is where the wires come in,
E
right?
divided by I. That is Ohm's law. So those three you should remember, learn them by heart. There is a way of remembering this, and you will have that picture in your book as well, the triangle. Here we have E, here we have I, and here we have R. All these three formulas are in here. E equals I times R, like the one on the top. I equals E divided by R, like the one in the middle. And R equals E divided by I. E is voltage, electromotive force, voltage. I is the symbol for current, and R is the symbol for resistance. Yeah, I don't know, we have a lot of that. Thank you, Bruce.
You're welcome.
Okay. Everybody learn these three formulas. You gotta know them. So, I'll write this off here. You don't have to remember my last name. So we have a voltage source of 12 volts. And we have a resistor here of 6 ohms. And we're going to apply that voltage source to this resistor. So we have 12 volts here, 6 ohms. What would the current be through that resistor? Remember the formula?
6.
Well, yeah, that's fine. But
Sure.
the formula is I equals E divided by R. So your answer is correct. 12 divided by 6 is not 6, it's 2.
Yeah, well, I tried.
Hey, like I said, there's no such thing as a stupid question or whatever, and trying is important. So, we'll come back to this formula, E equals I times R, and the other one was I equals E divided by R. So here's the formula. We wanted to know the current I going through the resistor here. So we take E is 12, R is 6, so 12 divided by 6 is 2 amps. Now you can test the other formulas actually by doing that. And now we know all three, but if you did not know the voltage that we applied to that, oh, I got the resistance, I got the current, so now I need to know E, the voltage. So you take E equals I times R, is 2 times 6 is 12. There's your answer. It all figures. Okay? Any questions about that? This is really basic and there should be no problem for anybody to do that.
And it's got R equals E over I, not E over R.
Oh, yeah, you're right.
Just
Printing mistake. Hey, that means you guys are observant. If you can catch me, I want you to catch me. If I make a mistake and you know what I do, let me know. All right? So, and I had this triangle here. I'll draw it on this side here. And you have it in your book as well. You put E for voltage on the top, and you can put I here and R there, or R here and I there. Doesn't really matter. There's the whole thing. So you don't have to draw all three formulas. You can derive it automatically out of here. Now, resistors. We have, I'm running a little bit ahead here, but the amount of power that is used in this circuit, and you will find that later in the book, but since we have these three now, I'm going to also give you the formula for power. Power equals E times I. So the amount of power being used and dissipated in this resistor is 12 times 2 would be 24 watts. Okay? So P equals 24 watts. E times I. So if you know the power and you know the voltage, you can also calculate the current. Because 24 divided by the voltage of 12, you know that the current is 2 amps. And now you know that, and if you didn't know the resistance, you can find out the resistance by R is E divided by I. 12 divided by 2 is 6 ohm. So if you, out of 3, if you know 2 of these characters, you can always derive the third one from it. Okay? All right, but most of the time we have more than one resistor in a circuit. We have circuits with 1, 2, 3, etc. resistors in series. And we're not going to discuss why they're in series. It is because of the electronic circuit was designed and we needed this. Also, if we need to have a particular resistor size or resistance, we don't have it in our junk box, you can make up that resistance by combining resistors. In the series resistance, let's say again, this is 6 ohm, this is 8 ohm, and this is 6 ohm again. In series, they add up, because you put one resistor and another one behind it and another one behind it. Those three make it more difficult for the current to flow. So the total resistance of an amount of resistors in series is by adding each individual resistor to each other. 8, 6, and 8 is 14, and 6 is 20. So now we have a total resistance of 20 ohms. So resistors in series add up to come to a total resistance. Very simple, and that's easy to understand. Anybody who does not understand that, it's very basic, really. Now we apply a voltage here. I'm going to make it very easy. We have a voltage here of 20 volts. Now, we have 3 resistors in series. What would the current be? Well, we know the formula for the current is I equals E divided by R. So we have the voltage divided by the total resistance, which is 20 ohms. So now we have 20 divided by 20. Again, we have a current flowing of 1 amp. Make sense? And I equals 1 amp. You notice that that current flows through every resistor, however many we have in series. So the voltage drop across this series resistor combination is 20 volts from here to there. Can we figure out how much voltage drop is happening across each of these resistors? Okay, so you look at the formula. R equals E times I, correction. The voltage, E is I times R. Since the current flowing through here is the same through all resistors, and it is 1 amp, the voltage across this resistor of 6 ohms equals E equals I times R. So we have 1 times 6 is 6 volts. Okay, 6 volts. Here we have 8 times 1 is 8 volts. And here again we have 6 volts. And we see how nice they work out that way. When we add 6 plus 8 plus 6, we come back to 20 volts. So the voltage drop across each resistor adds up to the total voltage applied to the series combination. We apply 20 volts here. We gotta have an amount of voltage across each resistor that adds up to a total of 20 volts, no less, no more. So that's how you figure out the voltage across each individual resistor by multiplying the resistance times the current that flows through the resistor. Now what we have done too, I needed a resistor of 20 ohms, but I didn't have it. So how did I arrive to a resistance of 20 ohms? I went through my junk box and I found a resistor of 6 ohms, and I found a resistor of 8, so I added them together, that's 14, so now I'm still short. So 20 minus 14 is 6, so I need another 6 ohm resistor. And now I have a resistor of 20 ohms, even though there are 3, but now you have a resistor of 20 ohms. So you've accomplished your goal. And we do that quite often in the hobby, by combining resistors and or capacitors to arrive to a value that we need, that we may not have in our junk box. Okay, so resistors in series add up to come to a total resistance. And it makes no difference whether it is 2 resistors or 3 or 15. If they're all in series, you just add them up to get a total resistance. All right, any questions about that? And I encourage you to study a book, to go through it, because all these examples are in there. But we just learned to figure out the total resistance of a number of resistors in series. We figured out the voltage drop across each resistor, and we figured out the current through it. But we had been given two items. We had been given the total voltage, and we had been given the resistance in total as well as each individual. And as long as you have that, you can calculate the current going through them, because in series they're all the same. The current is the same that goes through every resistor. Now, we had, of course, series resistance, but there's another way. We can have resistors in parallel. You think if we put them in parallel to each other like this, you think they all add up, the resistors, to come to a total resistance, like we did in series resistors? No, that would never work. Again, we apply, I'm not going to draw this line here to the other side, but we apply 20 volts across these resistors here. There's a current that starts flowing. And the current will, at this point, divide into three different currents. Here we have a current going this way, we have a current going this way, and we have a current going this way. And of course, this is negative, and this is positive. Because in electronics, the current flows from negative to positive. We still have the old conventional way where they say the current flows from positive to negative. But they have, in the meantime, discovered that it is actually the electron flow is from negative to positive. So to satisfy everybody, they say, well, the old engineers and all the people who have worked with positive to negative, we'll just leave it that way. We say the current flows from positive to negative, but the electron flow is from negative to positive. Isn't that confusing? So you go with the one or the other, whichever is to your advantage, depending in the circuit with either NPN transistors or PNP transistors. Sometimes it works easier for you to use the other way. The end result is the same. So, anyway, I'm going to make this 15 ohms, and this 15 ohms, and this 15 ohms. Okay, I got 20 volts here, and I got 15 ohms here, but I got three of them in parallel. When we put resistors in parallel, the total resistance will become smaller, will be less. Because it's like having three small garden hoses, and you put them like that in parallel. Because you have three small garden hoses, you're effectively making it now one big garden hose. Right? Now here, it's a little bit the opposite way, but because of three resistors in parallel, we're going to divide the current in three different paths. So the total resistance is less. And here is one thing that is a little trick that you should remember for sure. When you calculate resistors in parallel, the total resistance that you end up with is always less than the smallest resistor of the three, or the four, or the five, however many you have in parallel, or two. Now it's a little difficult to see here because we have them all the same, but we'll show you that in a bit as well. Another little trick, with resistors in parallel and they have the same value, it's very easy to calculate the resistance of the combination. We have 15 ohms, all three the same, and we have three resistors. So now we divide 15 by 1, 2, 3, is 5. So now we know the total resistance of this combination is 5 ohms. Well, that proves, of course, that the total resistance is less than the smallest, but you don't have a smaller one here, they're all three the same. But this is how you can calculate the total resistance or the resultant resistance, as it is sometimes called. If you have resistors in parallel of the same value, you take the value of one resistor divided by the amount of resistors you have, and you come right away to the actual resultant resistance. It's easy to remember, but how often would you get three resistors in parallel that are exactly the same value? Not that often, not in real life. But it is something that you can remember. So here we have 5 ohms as the R total. 5 ohms. So can we calculate the current going through here? I equals E divided by R. E is 20, R is 5. 20 divided 5 divided into 20 is what? 4, exactly. So I is 4 amps. Now, that is the total current flowing through the whole system. How much current is going through here? How much current is going through here? How much current is going through here? Again, because all 3 resistors are the same, the way you calculate that is you take 4 amps divided by 3, whatever that happens to be. 1 point something. So if you knew only the currents flowing through each resistor, what would the total resistance be? You just add all 3 currents up, and there you have the total current that flows through the circuit. So it's very easy to see if you have resistors of the same value. Now it's going to become a totally different story if we are making these of a totally different value. This is 15 ohms. This is, let's make it 5 ohms. And this here is 7.5 ohms. Now we're going to have to calculate the total resistance or the resultant resistance. You know, from math, when you went to school, the way we used to do it before we had calculators, you have 15 and 5 and 7.5. So 15, 5, 7.5. You had to come to a common denominator, right? So you had to come to a common denominator that all 3 can be divided in. Well, the closest common denominator here is 15, because 5 goes into 15 3 times, and 7.5 goes into 15 2 times, right? So you have 1 15, and you have 3 15, and you have 2 times 7.5, that's 15 as well. Now then you add these up. 1, 3 is 4, and 2 is 6. And then you do it that way. But there is a lot easier way. Don't have to remember that. I just showed you that's how we used to do it. And a lot easier way to do that. Remember, on the exam you are allowed to use a calculator with the basic functions. Adding, subtracting, multiplication, dividing, square root, percentage, that you probably don't need to do this anyway. It is not allowed to have any memories in it. That's where you can store things, where you can store a whole formula in. That is not allowed. Correct, Bruce?
Correct.
Right. So you can use a calculator. Well, there's a lot easier way to do this. The actual formula, I should write it down, is R how it's done. 1 divided by R total equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. We call these R1, R2, R3. If you calculate, does anybody have a calculator here with them? I'll use my cell phone here. You got to know, of course, how to use your calculator in the first place. So here's a very basic calculator. So first we're going to say 1 divided by R1. So I literally do that. 1 divided by 15 equals 0.0666. Now I add that into memory. So I say memory plus. Clear? 1 divided by R2. 1 divided by R2, which is 5, equals 0.2, 0.2. Add that to memory plus. Clear it again. Now I take 1 divided by 7.5. 1 divided by 7.5 equals 0.13333 ad infinitum. Add that to memory plus. Clear it. So now I say 1 divided by our total, which is 1 divided by memory read, okay, equals 2.5 ohms. There's our answer. So it's very easy to do. So our total is 2.5 ohms. Do we right away see something that I mentioned earlier that you got to remember? That in parallel resistors, that the total resistance, the resultant resistance is always less than the smallest one of these resistors. What's the smallest one here? 5. What's the total resistance? 2.5. It's less than that. Happens to be exactly half of it, but it is less than that. Now you've proven yourself, at least you've done the calculations correct. Whether this figure is correct, well, you assume because you used your calculator. They don't make mistakes, right? So, but that's how easy it is. And it doesn't matter whether you have 2 resistors or a whole bunch of them. It makes no difference. 1 divided by R total, 1 divided by R1, plus 1 divided by R2, plus 1 divided by R3. And you just do the 1 divided by 15 on your calculator, you add that result to the memory. And then you do the second one, because you have to add them together. Do the second one, plus memory. Then you do the third one, plus memory, add it into memory. So now you've, in your memory, the figure of these 3 calculations. And you clear your calculator, not your memory, just the answers. And then you go 1 divided by memory read, and there's your answer. Very basic, very simple to do. So if the resistors are the same value, you take the resistance value of 1 divided by the quantity of resistance that you have, and you got your answer. You don't need a calculator for that. Except if it's 3 of 2.125, well, you may not want to do that anymore. But that's how easy it is. But if the values are different, that's how you do it, with your calculator. Okay, any questions about this? Now they show a different formula in the book. If you have 2 resistors in parallel, they use like R1 times R2 divided by R1 plus R2. That's only good for 2 resistors in parallel. So that's how you can do this as well. You can do these 2 first, 15 and 5. So you do 15 times 5 divided by 15 plus 5 gives you the answer. And then you do the same thing again. That becomes 1 resistor then. And then you do the same thing with this one, and you come to the same result. But this is easier, especially with more than 2 resistors in parallel. And you could call this R total or resultant resistance, whatever you want to call it. I always call it R total, yes.
I'm assuming that equation only applies like if they're in parallel,
Yes.
right?
Yes.
That's the only time you bring that up?
That's the only time you use this formula, when the resistors are in parallel.
So if they're in series, like you said, you just
Then
add
you
them up.
just add them up. Okay. So that's, any more questions, yeah?
I got a different answer for our total.
Okay. What did you have?
I don't know if I'm.
Okay, let's start it over again. Clear your calculator and your memory. And if anybody else have a calculator, let's go through that.
Oh, no, okay, sorry, I figured it out.
Okay.
I forgot.
Well, let's
One
go
divided by
through
our
it.
total.
What did you do wrong?
I forgot to divide 1 over our total.
Oh, okay, right,
Yeah.
yes. Now,
That's
don't forget, that's why I write it down, so
Yeah.
that once you have done these three, then you bring up what you have in memory, and then you, first of all, you do 1 divided by, and then you bring up what you have in memory, and you get the answer.
Why would you do parallel? Like, what would be a real?
Well, let's say, in this example, I need a 2.5 ohm resistor, but I don't have one. So I'm gonna go through my junk box and
Yeah.
I got a 15 ohm and a 5 resistor. You calculate what the parallel resistance is of that, and then you can eventually come to the result of what you need.
So they're just all workarounds?
Yep,
Than
yeah.
the real part?
And as a hobbyist, you do that, you know, at times. That you have your junk box of resistors that you took out of an old television or an old radio that your grandma used to have and throw it in the garbage. And you take it out of there, you take all the resistors and capacitors out of there because you know you're going to use them in the future.
So if it's starting off at 20 volts, are all 3 resistors getting 20 volts at the same time?
Yes, they are,
Okay,
yes.
and then it breaks down from there.
Then it breaks down from there. So you have 20 volts here, that means there's 20 volts across this resistor,
And each
20
one,
volts across that, and
at the end of each resistor, that 20 volts is now stepped down, what it's
well,
corresponding to.
it is 20 volts, of course, here. Would be plus 20 volts here, it's negative. You could say there's no more 20
Yeah.
volts here.
That would be lower.
Yeah, well, the 20 volts is across that, so.
Yeah, okay.
that's,
So the volts are going over, like, it's exactly, like, say, if it's 20 volts. Is 20 volts for each resistor that's gone through?
No,
Whether-
no, the voltage doesn't go through it. The
The
voltage is parallel to it. It's a load that you put on. Okay, I'll take this away, and I will draw it the way I drew the first one, and that is,
So I was thinking you might do that to power different,
so
Take
here
a
I
second
have
light.
20 volts, positive, let's say, and the
See.
negative. So there's 20 volts across this circuit.
okay, so it's 20 positive, 20 negative.
Well, no, not 20 positive, 20 negative. If you have a battery, it has a positive
Right.
terminal and a negative terminal,
Great,
right?
yeah,
So that's what I drew here.
okay.
In this case, it doesn't matter, you could reverse it, this could be positive and that could be negative, it really doesn't make any difference, because it is just a resistance circuit and polarity is not important here. If you had solid state components in here, then the polarity would be important. But what you see here is that you put, I can draw it even another way, and that maybe that makes it a bit easier to see yet. Otherwise, I would have to draw these sideways. And I have 20 volts here. I'm going to leave positive and negative out, doesn't matter. Now you can see that there's a 20 volts supply, whether it's a battery or a power supply or whatever, that is across those 3 resistors who are in parallel. So the same voltage is across each individual resistor.
And one would do, like I was, in my head I'm thinking that would be an example, let's say you had 3 lights that you wanted to hook up at different brightnesses. You would hook them up to each of the resistors, right?
Yeah,
And
you
then
could,
creating
yes,
different brightnesses?
yes.
Okay,
Yeah.
I just wanted to make sure.
If you had 3 lights and they each said, let's say they're each 10 watts.
Yeah,
Well, you don't want all 3 to be the same. You could use different resistors and we would all 3 go at a different brightness. Yeah, that's an example that's to illustrate it. But in this case, we wanted a resistance because we didn't have a 2.5 ohm, and we figured that with these 3 we can make a 2.5 ohm resistor.
okay.
Okay, so now we've seen the series resistors, and we've seen the parallel resistors. Now there's another combination, and that is what they call series parallel. So you have a resistor here in series with those three parallel resistors. Now you're going to have to figure out the total resistance of that. Let's say this is a 10 ohm resistor. Well, how the heck am I going to figure that out? Well, the first thing you're going to calculate is the resultant resistance of these three in parallel. And once you've done that, those three resistors, in essence, become one resistor. Because those three, 15, 5, and 7.5 ohm, you now calculated, it came to, what was it, 2.5? 2.5 ohms. Now you got a series chain. So you add 10 plus 2.5, so now the total resistance here is 12.5 ohms. Simple. Now you can have really weird combinations of series parallel, you know. You could have a combination like this. Okay, here's a series resistor. Here we have a parallel resistor. And here we have 1, 2 series resistors. And here we have and another one in series. And these all three come together. So what do we have here? We got 2 in parallel, we got 2 in series, and then we have this resistor plus this combination plus this combination in parallel. So how would you approach it to calculate that? Where would you start?
Most complicated one?
Which is the one at the bottom?
Yeah, the parallel.
Yeah, so these two resistors you figure out first as a parallel combination, okay? And once you calculate that, remember again, the resultant resistance will always be less than the smallest of these two. So if this one was 5 and this one was 2, it would have to be less than 2. So if you do your calculations and you come out with a figure that is less than 2, the big chance is that you are correct. So that now, these two you've calculated, and they become now one resistor. So now we're going to make it easier yet. We're going to add these two resistances together, and that then will become one resistor. And then we add these two together, and it will become one resistor. So what do we now end up with? A whole funny combination. We got 3 resistors in parallel. So you take that fancy formula in your calculator, and you calculate the resultant resistance of those two, and in the end you end up with only 2 resistors in series. Add them together, and now you have only 1 resistor left as the resultant resistance. So in a series parallel combination, you break the calculations down. You start with the parallel ones, build them down to 1 resistor. If there's another one in series, you add them together. Now you have, again, 1 resistor. So,
Now, how often do you find that in manufactured products?
not
This
really.
is just for tinkering?
No.
Kind of?
This is just so that you understand Ohm's law.
Okay.
That you know how to calculate voltages across resistors, that you know how to calculate the current through a resistor, and if you have both of these, but you don't know what the voltage is like, you know how to calculate what the voltage will be. So let's call it exercise.
Okay.
Because in the manufacturing process, they would never use this combination. They just make one resistor that is the actual resultant of what we just calculated. Okay? But there are instances, well, I'm just going to mention this, and we're not going to elaborate on it. Boy, I'm a real good drawer here. And so here we have 4 resistors in this combination. That's like a Wheatstone bridge. I don't know if you've ever heard of a Wheatstone bridge. Okay? But in here you could put a meter in between here, voltmeter or ammeter. You got 2 resistors here, you got 2 resistors there. if these resistors are all equal, perfectly equal, 1% or 0.5% tolerance, and they're perfectly equal, there's no current flowing through this meter. That's called a Wheatstone bridge. So you could take this resistor out, make it a variable resistor, calibrate it, and you can do wonderful things with it. So, but we're not going to elaborate on that. Okay, what time are we doing?
5 minutes
To 8.
we can have a break now if you want.
Yep, yep, we can start our break. I'll give you, after the break, I'll give you one example where you would use two resistors. Alrighty, we're going to start again. Talking about resistances, of course. These are resistors made for our purpose, because we may need them in the circuit. We're all familiar now with the resistance code, right? With the black, brown, red, orange, you name it. And so here we have a resistor that has orange, orange, brown. So that would be what, 33 ohms or 330? I forgot. I have a little handy thing that I bought at Radio Shack about 35 years ago. It's a little card with 3 wheels or 4 wheels, and you dial until the right color shows up, and then it tells you what the value of the resistor is. So you don't see them anymore. Anyway, all these resistors that I showed around are made for a specific purpose. The ones that are ceramic or have a ceramic body, you can count your socks that they are like, first of all, a fairly powerful resistor. They dissipate a lot of heat, and that's why they are built onto a ceramic body. But what else is resistors? Wires are resistors too. And if you want to carry a high current, you need a thick wire. So very small wires can only carry small currents, because you know what happens if you have a very small wire, like this little wire, and you want to push 20 amps through it. Well, it acts as a fuse, and it'll go up in smoke. See, you let the smoke out and it doesn't work anymore. So, I forget about this. Is a 24 AWG. Anybody knows what AWG stands for? American Wire Gauge. Okay, American Wire Gauge. It's a number. The number gets smaller, the wire gets bigger. Believe it or not, it's kind of opposite, but at any rate. So this is a number 24. This is a number. I can't see it, but this is probably a number, who knows, 20 or 18. All the way up to is a number 6, a number 8, and this is a number 4, and this is, yeah, it's about the same thing. But also there are differences. See, this is pretty stiff, because it is a stranded wire, but it has all thick, solid copper wires. This one here is about the same kind of wire, but look at this. And it is also strands like that, but each of the strands consists of strands as well. So you can see the difference there. This one is pretty stiff. This one's pretty soft, flexible. Again, because it is of multiple strands. And here we got a real heavy-duty one. That's double aught, 2-aught, 2-0. It's a very thick wire. That's, you can guess what, I don't know if this was actually shorted at one time and it kind of welded itself together, or whether that was probably fused that way on purpose. So, just to show you all the different sizes of wires available. You can imagine that thick wire can probably carry a couple hundred amps in current. And it would be used in the industry, apartment buildings, who knows what. But they all have resistance. That one has very small resistance. That thin wire here has small resistance too, but if you get a great length of it, you get a large, fairly large resistance as well. So So let's say you have this wire here, you've got a fairly high voltage, you need to limit the current through it. You could use a resistor in series with it to limit the amount of current going through it. Okay, why would we use resistors in series? Well, for example, we have a power supply here, and it has, I don't care, 10 volts. But you need 5 volts. So how would you get 5 volts? Well, you make a series resistor of 2 resistors, and at that point, how large would these resistors have to be? Here's 10, here's 5. In a sense, it doesn't matter how large they are as long as they're both the same. If they're both at the same value in resistance, then the voltage here at the junction of them would be half of this voltage. But if you wanted a lower voltage than 10 volts, let's say 3 volts, then you would have this resistor larger than that one. So you calculate the current going through here, and you can calculate the voltage across each resistor. If this resistor is larger, it'll drop more voltage than this resistor, which is smaller. So there is a way that you would use 2 resistors in series to get what's called a voltage divider. Does that make sense? So now between here, let's call this the common, or let's say the negative, and this is the positive. And now between this point and that point, we have 5 volts. So that would be a quick and dirty way to make smaller voltage for whatever purpose. Charge your cell phone or who knows what. Now you can make this chain as many as you want. You could use another resistor here and another resistor here. And now you have a different voltage at this point and a different voltage at that point. That could be 5 volts, 3 volts, 2 volts, and then it's the common again. So here you have a bunch of resistors in series, and because they have different values, then they have different voltage drops across each other. So they have a voltage divider that provides you with multiple voltages. So you wouldn't want to draw a lot of current through here, because the more current you're going to draw, the voltage is starting to drop as well. So, but there's an example. I think we're going faster than we actually get. We're almost at the end of the chapter here. But that is okay. I have a few examples to show you. Well, we've already done the series parallel combinations. And the next one here, we're coming to this, this power. Power equals voltage times current. And you see on the bottom of page number 311, you see that wheel with all these funny things on there. Well, you have the same thing on the sheets that I handed out. The one is for Ohm's law for DC current, direct current, and the one on the right hand side is the Ohm's law for alternating current. You don't have to worry much about that because we're talking here about impedances, inductive and capacitive reactances, so you don't have to worry too much. But the one on the left is very handy, because in the center you see P, I, E, and R in the center circle. And then all the radiuses give you various formulas to calculate, like the watts, for example. On the left, above the 9 o'clock, it says E times I. Well, it implies E times I. They write EI with nothing in between, but that implies multiply, E times I. So that would be power. Also, I squared divided by R, or times R, would also be power. And then there's E squared divided by R gives you the power. So again, as long as you have 2, you can always calculate the third one. Now, you don't have to, well, it'd be nice to remember all these formulas, but if you don't remember, like E squared divided by R, how the heck am I going to do that, you know? You can always, if you have the voltage and you have the current, you can calculate the resistance. Or if you have the voltage and the resistance, you can calculate the current. Once you've done that, you just, oh, power, it's easy, P times I. So you don't necessarily have to remember these formulas like E squared divided by R. You can always get to the part that you need in the easiest way. So P equals P times I, which evolves out of that E equals P divided by I, and I equals P divided by E. These are the three main ones which you can get out of the one formula. You can make them one like that too. You go like that, P, and you go E and I. P is E times I, E is P divided by I is P divided by E. There you get all the three formulas in one triangle. Learn these, become familiar with them, don't disregard them, because there will, I can almost guarantee you, there will be a question on the exam. And as Bruce indicated at one point as well, that don't get too worried and you say, well, this looks so complicated, I don't think I can do that. Stick with it and go through the book, try to understand it, and you will find that once you go through the exam that it wasn't nearly as hard as you now think it may be. There will be some small calculations. They may give you a series resistor combination or a series and parallel. Just break it down into, like parallel ones, calculate them so that it becomes one resistor. And if it's in series with another, you add them together and you have it. And they're not going to use very complicated ones to begin with. Another thing, and for this evening, it doesn't apply so much to this evening, but if you go on, especially like capacitors and inductances and transistors, electronics is also a little bit like religion. There are things you do not understand, but you just blindly believe that's the way it is. You know, the engineers have calculated and figured all these things out, and they've proven it scientifically. So if you don't know exactly understand from what the magnetic field will do as an inductance and the voltage it induces and which way it flows, I understand. Don't understand that. Don't worry about it. Just accept it and believe that it is the case. A little bit like religion. Alrighty, now we have used these resistors calculating. We can, again, in practice, we can make use of that. Let's say you have a power supply of 12 volts. You have a nice little light bulb. I always draw a light bulb like that. But it's a 6-volt bulb. Well, you know, if you're going to hook this light bulb up to 12 volts in maybe 2 seconds, and then it's poof, you let the smoke out and it doesn't work anymore, right? But what are you going to do? Well, here's the light bulb, and we're going to put a resistor in series with it, and we hook that up to 12 volts. We know that this is 6 volts. We know that we have to get rid of the other 6 volts. So we get rid of the other 6 volts by getting a resistor. And it has to be also 6 volts, right? Because that's what's left. So we can now calculate the current, right? 6 volts and 6 volts is 12 volts. And here is 12 volts. You know, the resistance of the current going through here would be 12 divided by 12 would be 1 amp. So what would be the resistance that you need here? R equals E divided by I. So 6 divided by 1, it would have to be 6 ohm. I used very easy figures, but you could put any figures in there. This could be a 3-volt light bulb, and you could have 20 volts. The same principle applies. 6 volts across this light bulb, and 6 volts across this resistor totals 12 volts, which is the supply. Okay? So you calculate the current, then you calculate the resistance, and you're all there. So there's an example how you would use the formula of calculating resistors in series. You will, in one of the other classes, you will learn about LEDs. I don't draw any arrows that show that there's light coming out of it. LEDs, they actually run at about 1.6 volts. Again, you have a 12 volt supply. Well, hook that LED up to 12 volts and it will be bright for a couple seconds and poof, you let the smoke out. It doesn't work anymore. It's always that smoke that makes it work. So, you do the same calculation. You know there is 1.6 volts across here, and the power supply was, let's say, 12 volts. Now you have to get rid of 12 minus 1.6 is what, 10.4 volts? So you've got to have a resistor here that gets rid of 10.4 volts. So you calculate the current going through here, and then you can figure out what resistor it has to be to drop that voltage. Okay. I'm going to show you a few things here, because we are ahead of ourselves. I have here a power supply that I designed and built probably 25 years ago, and it is a constant current power supply. That means no matter what the voltage is that it puts out, if I set this for 25 milliamps, no matter what I hook up to it, it will put out 25 milliamps. Until, of course, there's not enough voltage anymore to do that. But the voltage here, it's been on for too long, so it switched itself off. Okay, 2.5 volts. I have a relay hooked up to this power supply. That relay at 2.5 volts does not work. It does not energize. I'm going to increase the current, and you can see, maybe not everybody, but you can see when I increase the voltage then, or the current, it goes up to a point when the relay energizes. Bingo, you heard the click, now the relay energized. So now it will tell us the minimum volt that we require to energize this relay is about, let's say, 7.5 volts, because that's the voltage now across the relay, 7.31. So there's a real advantage of that. What would the current be? I think it shows about roughly 75 milliamps. Now here we come to another thing. We have how many volts here? Let's make it to up to 7.5 or 8 volts to make it nice. Okay, wow, look at that, 8.00 volts, and the current here shows about 80 milliamps. So we have 8 volts and 80 milliamps. Can we calculate with these two parameters what the resistance is that flows through that circuit? Remember, R equals E times I. Sorry, before you catch me. I didn't draw it up off there for nothing. E divided by I. Okay, we have the voltage, E, we have the current, I. So now what we do, we just divide 8 by 80, and now we get the resistance. That's right, we will not be able to do that. Remember, when you do calculations with resistances, ohms, voltages in volts, and current in amps, you've got to use these basic figures as they are. So if I want to find out what the resistance is, I have to either convert this from milliamps to amps. 1 amp is how many milliamps? Anybody know that?
10,000?
Yes. Milli stands for 1,000. So, don't forget, 1 amp is 1,000 milliamps. 1 amp is 1 million microamps. There's another sheet that I gave you, and it's this one here. Right on. It's called engineering or scientific units. If you go to the bottom line and you see the dashed vertical line above it, it says base unit. Let's say that is 1 or 0 or whatever. But if you go to the right, it shows milli, micro, nano, and pico. And you also notice that under milli it says 10 to the power of -3. That means that this becomes smaller, milli. 3 power of 3 is 1,000. So if that was 1 amp, then at milliamps it would be 1,000 milliamps. If it was a microamp, it would be a millionth of an amp. Okay? 10 to the -6, you notice that they all increase by factors of 3, 10 to the power of -3, 10 to the power of -6, 10 to the power of -9, and 10 to the power of -12. If you go the opposite way, from base unit higher, then you go 10 to the power of 3. So from 1 volt to 1,000 volt is a kilovolt. A kilovolt is 1,000 volts. Okay? One amp equals 1,000 milliamps. And you write this in a small m. The amps you always write with a capital letter. Now, if you have 1 amp and you want to make it 1,000 amps, then it becomes 1 kilo amps. Okay, 1,000 grams. Well, we don't do metric here, right? Or do we use grams and all? Yeah, a kilo is 1,000 grams. A kilo amp is 1,000 amps. Okay? So if you go from the basic unit larger, 1,000 times, it becomes 1 kiloamp. If we go again 1,000 larger, it becomes a 1 million amp, a megaamp, you could say, I guess, megaamp. If you go another 1,000 times smaller, it becomes a microamp. You go another 1,000 times smaller, it becomes a nanoamp. You go another 1,000 times smaller, which is 10 to the -3, it becomes a picoamp. So you have to learn how to convert from one to the other. It's really easy. 80 milliamps. If you want to go convert that to amps, which is 10 to the power of -3 or +3, you go 1, 2, 3. So it is 0.08 amps. Now we can do our calculation. We say 8 divided by 0.08. What does that come out to? Is that 100?
Yeah.
Right. So supposedly the resistance of that relay because it has 8 volts, it's crept up a little bit, but if it has 8 volts across it, and the current we had was 80 milliamps, which is 0.08 amps. I can do it by heart because I've done it so many times, which is 100 ohms. Okay, now another thing, we're going to measure this resistance of this coil. But you notice also it took about 8 volts to get the current through here, create a big enough magnetic field to energize the relay. Because if it wasn't enough, okay, we're going to turn it back up again until we hit a click. There we go. It energized, and again we were sitting at 7.22 volts, but I wanted to make it a nice round figure, so I do it. So increasing the voltage, the resistance is fixed of this coil. That doesn't change. Whether it's 50 ohms or 100 ohms or 200 ohms, that is a fixed value that does not change. So if you increase the voltage, what is the current going to do? If I equals E divided by R, this remains fixed, doesn't change. So if I'm going to increase the voltage, I has to increase as well. Okay? And you can see that here on this little meter, because if I'm going to increase the voltage, what I do now, you see the meter goes up, current becomes larger. So we calculated 100 ohms, right? All right. And by the way, it takes less. I'll energize it again. Now I'm going to decrease the voltage, because now we have a magnetic field that holds the clapper in. I'm going to decrease it and decrease it. Now we're already at 3.5 volts and it's still energized. Until well, it even holds at 2.5 volts. So there's a typical characteristic of relays or any solenoid coil. Once it has enough of magnetic flux to energize, I call it the clapper with the contacts, when you reduce the voltage, it holds for a long time. The voltage got to drop quite a bit lower for it to de-energize again. I think we're just disconnected. Okay. Let's measure the voltage now, or the resistance. I brought another meter here. If you are doing any experiments at all, and even if you don't, as a ham operator you should have at least a VOM, a volt ohm meter. In this case it's a digital meter. The volt ohm meter, what we used to call multimeters, whatever, used to be the black case with a meter that has a needle that moves up and down, called the Darson Fall meter. There was a gentleman who invented it. They're still around, but mostly now digital meters. This one I purchased, and don't look at the way the wires are. I use it so often that the insulation started to break. But this little meter, it does AC volts, DC volts. It does test 9 volts and 1.5 volt batteries. It measures current from 200 microamps up to 200 milliamps. DC volts from 200 millivolt to 1000 volts. It measures resistances from basically from 0 up to 2000 kilo ohm, which is 2 mega ohm. Okay, and it measures also 10 amps. It also tests diodes, and it tests the gain of transistors. This little meter, if you're lucky to get it on special, $4 and maybe 50 cents. There was a time that you probably spend $100 for this. what's it called, the store in the States. They don't have them in Canada. There's none in Sault Ste. Marie. Harbor Freight. We may have all heard of it, we may have not, but the nearest, well, I shouldn't say the nearest one, but when I visit my son in Grand Rapids, I always make a trip to Harbor Freight, and I always find something that I need, you know, because I see it, oh, that's nice to have. I probably need that.
They have one
You
in
know,
Traverse City.
2 years from now, Traverse City, yeah. And they have these meters on the shelf, and you wouldn't believe how often they are on special. There's two kinds, there's this one, and there's another one that has a little push button where you push it, a nice orange light comes on, so you can use it in the dark too. I think they're $1 more, or $2 more. Now, these are basic, well, it's not a basic meter anymore, because you can do a lot of things with it. But I don't think it is a meter you would want to use as an electrician and measure like 550 volts with it. That was not the purpose of these. These are a little digital meter for hobbyists who want to measure the voltage on the battery in your car, whether it's 12 volts or 10 volts. You build a little power supply. That's what you may use to measure the voltage with. You've got a couple of resistors where the color codes have kind of worn off. What's the resistance of it? So you use this little meter to figure out what the resistance of that resistor is. That's what the purpose is for hobbyists, not for professionals. If you are a professional, you have a meter like this that is approved, or a meter like this, and that has a brand name that a lot of people may be aware of. It's called a Fluke. It's no Fluke by no means, but it is a brand name, and that's a high quality meter. I've had this probably for 20 years now. My wife often scolds me for that. I like calculators and I like digital meters, so I have a number of them. At one time I bought 5 of them, and I got 2 left. Because at the club meeting one time, something, I may have been passing an exam. Whoever passed the exam first, I gave him one of those meters. You know, $4. The guy went in heaven because he got a digital multimeter. So, anyway.
I'll pass that by Brent and see if he'll see. Could be
Well,
students who pass a meter.
You know,
Something to look forward to.
$4.50, whatever, you know, you can go wrong. And the AC measuring is kind of crude. You've got 2 ranges. The first one goes to 200 volts, perfect for measuring the voltage in an outlet. And the next range is 750 volts. So you can still measure in a radio that has tubes and it may have 600 volts on a plate. You can still measure that, but be careful. All right, we were going to measure the resistance of this relay, the coil. There. That's how I use 2 hands. And the resistance is 103 ohms. 103. We calculated it to be 100 ohm, roughly. Now this at 8 volts. Here on this meter, which is by no means accurate, it showed up at 80 milliamps. And we did the calculations and it says 100 ohm. I measure 103. Perfect. The tolerance of this meter and the tolerance how I calibrated this with this potentiometer, maybe 10%, so it's pretty accurate. The big advantage of a power supply with a constant current, you hook this up too many wires. But that's what you need if you want to display both meter and for voltage and other things. Okay, let's make sure everybody close your eyes because I'm going to short this out. Did it change down there? The meter? Well, it comes on and goes off. But it stays at the, here I'm going to increase the current. Now it is, I think, about 50 milliamps. It's a constant current power supply. Whether I short it or whether I put a resistor across it, still puts 50 milliamps through there. So it's a handy power supply for charging it, nighttime time. If you have a Nikon battery that is 200 milliamp hour, we charge it with 20 milliamps. The kind of the going rule is you divide it by 10, and that's the figure that you can charge it at over a period of time, 10 hours or whatever. So that's perfect for that, and I've charged many batteries with this. If I put 10 batteries in series, it will still supply that amount of current, because the power supply voltage in total is about 48, 49 volts. So you can have quite a few 1.5 volt batteries or cells in series before you reach the 50 volts. So it's really nice. I had this LED light hooked up here, and in the meantime it has gone out. So this capacitor, tonight's lesson is not about capacitors. That would be the next lesson, which I used to teach as well. But since I'm coming from Deborah, Brent was so nice to do that for me, so I don't have to drag the town back and forth a number of times. I'm going to charge this capacitor, which is 60,000 microfarad, and you will learn what that is. And I'm going to charge it. I'm going to start here with, okay, I got, right now I got about 25 milliamps going through there. But this is such a large capacitor, and it's only charging at 25 milliamps, we can probably sit here for the next 15 minutes before it charges it all up. So I'm going to increase it. Now I'm at 100 milliamps, and it's still showing 100 milliamps. So that capacitor is so large, it takes a large amount of current to charge it, or time. So I'm going to increase it by 2, and now I'm charging it here at 120 milliamps, and it's still charging. You will learn that now it starts to drop. That means the capacitor is now reaching its point where it gets almost totally charged. Now I'm going to back to the other one here. So it's showing now at 10 milliamps, going down, going down. It reaches now maybe 6 milliamps, 5 milliamps. Take it from me, in theory, a capacitor will never reach full charge. But it is so close to it. They consider a capacitor charged if it reaches 0.63 volts of the power supply. So if the power supply voltage is 100 and it reaches 63 volts across the terminal, it's considered charged, because they have to pick something. Okay. Now, a capacitor is not like a battery. However, a capacitor, once it's charged, and I disconnect it, it holds that charge for quite a while. It can hold this for a long time. And there is a lot of energy stored in this capacitor, because the capacitor being 60,000 microfarad, that stores a lot of energy. When I was back in Holland initially, I was studying for an electrician, which I did become. We had to build little circuits in a little cubicle on a mezzanine, and the teacher gave us pieces of wire, and he was a stingy bastard, because he measured every piece of wire. Oh, you need one that is 12 centimeters long. He gave me a piece of 12 centimeters long, and if you brought it back, it better still be 12 centimeters. You were going to be cocky. Anyway, the way how we got back at him, we put a big capacitor like that, charged it up, and then we put it in his pocket. Not that big. And we then went, and of course he caught on to us. He knows everybody did that, every class did it. And he goes, and then he gets a shock with the capacitor charged up. But we got one on him. We put, there was a safety transformer, and we took the output, it was about 80, 90 volts. And we put it on the railing, because the mezzanine had a stairway going up with a steel railing, iron railing, so we put the railing on the charge. And you got a bit of a joke out of it. I really got a little kick out of it. Anyway, he was really stingy, but I guess he had a limited supply of money, so every piece of wire counted. Anyway, this thing has been charged now, and it's still holding the charge. Let's measure what the voltage is on that capacitor right now. And it's still, yep, it's showing 48.1 volts. And this supply puts out about 49 volts. So it's still holding that voltage pretty darn good. I can hook up this little LED light to it, and I tried it at home first. I forgot to put the resistor in series, and the smoke came out of that resistor here. As you can see, it's all black, but it didn't burn out on me, so I was kind of lucky in that aspect. Positive to positive. LEDs are polarity sensitive. There we go. There you see, it's not a battery, but a capacitor holds a charge for quite a long time. And it holds the charge long enough that it lights up this LED. And if we now put the voltmeter across it, I like to do things like that, experiment with them and show the class what happens. Okay, what is the voltage now? 39, you can see it dropping. The voltage is dropping. See how the voltage is dropping? By 0.1 volts at the time. And it goes fairly fast because, you know, it takes current to light up these LEDs. So you say, well, just 3 little LEDs, that's not much capacitance, right? Or capacity, I should say. So we'll charge this one back up again to full voltage. And this one here, this one there, make sure I got the polarity correct, because an electrolytic capacitor has a polarity. And if you hook it up wrong, you can destroy it. So make sure you got the positive to the positive. And this is a black wire, but I marked it with red tape, so I wouldn't make the mistake. So it's charging it again. See, the needle is again at full current. So now it's charging up a lot faster, because all it does now is replenish what we took out by using the light.
Now, at what point will that capacitor blow?
Well, it won't blow.
Okay.
It would if you were to apply a lot more voltage. The working voltage of this capacitor is 75 volts DC current. So it is 60,000 microfarad at 75 volts DC is considered the working voltage. Now there is always a tolerance and you can go a little higher, okay? So, all right, well, let's consider this is now fully charged. And now I'm going to show you the capacity of the capacitor. Where is it? I always use the same wire for this. And I'll tell you in a moment why. So we charged it up with the voltage, and it's quite a voltage in here, quite a capacity. Okay, there we go. Smoke? No, it doesn't work at all. It still works. But if you see the terminals here, they're all black. And this one has fused itself. It's literally melted the metal of the crocodile alligator clip. I can't open it anymore. That's why you know why I always use the same one. So now this capacitor is discharged. I can guarantee you that there probably was a current flowing in here, and this is warm now. There probably was a current flowing in here, maybe, who knows, 100 amps. Just very, very briefly. Because this capacitor had, let's say, 49 volts in there, was instantly discharged in 0 ohms, so you had a very, very high current flowing. So that was my little demonstration. And I think we're at the end?
Yes.
Okay.
2 minutes past.
Alrighty, good. 2 minutes past, overtime.
Yes.
Okay, good.
Well, thank you very much, Tony.
Okay.